Hello, my name is Rob Weber. I'm currently a postdoc at Caltech, supervised by Joel Trop in the math department. And I work on randomized numerical linear algebra. But this is about earlier work with Jonathan Weir, one of the organizers of this workshop, and our collaborators in chemistry, where we were looking at a particular application of randomized numerical linear algebra ideas to quantum ground state and lately quantum excited state calculations. So get excited. So the plan for the talk is to give quite a lot of introduction and to focus in depth on single eigenvalue problems first. Because I think if people leave this room with a good understanding of the single eigenvalue case, that's already a success story. Our later work to extend the basic methods to multiple eigenvalue problems unfortunately does involve some technicalities involving orthogonalization. Orthogonalization is really rough. And I'll try to make it as easy on you all as possible, but there are some technicalities involved there. And there are, at this point, a number of references. We've actually written 4 papers. The first 2 were about single eigenvalue problems, and they're available in JCTC. We recently got our first math paper on this topic accepted into CISC, so that'll come out this year. And then we have another chemistry paper that may well be published in JCTC to complete the series. So let's hop into it. The background for looking at these issues is that all the time in scientific computing, we need to solve extreme scale eigenvalue problems. So well beyond just quantum many-body calculations, large eigenvalue problems are everywhere. And these could be 1,000,000 by 1,000,000 matrices. They could be 1,000,000,000 by 1,000,000,000 matrices. Traditional deterministic methods will definitely be too expensive. In my field of randomized numerical linear algebra, there are random projection methods, which are maybe 10 times cheaper, but that's not going to take you to 1,000,000 by 1,000,000, 1,000,000,000 by 1,000,000,000 matrices. And so I would argue that Monte Carlo methods, Monte Carlo-based methods, like the ones I'll talk to you about today, are pushing the limits of the biggest examples that scientists can handle, where you see in the literature quantum chemistry matrices that are as big as 10 to the 108 by 10 to the 108. And then Monte Carlo sampling, is also applied to problems in continuous space, which is formally infinite dimensions. You are evaluating a density everywhere over Euclidean space, and that could be an infinite dimensional vector. So these methods are pretty cool in pushing the limits of dimensionality. Our motivation as mathematicians, I guess me and John in particular, in looking at this problem is we think the methods can be pushed further, but first their limitations need to be addressed. There are some inefficient implementations, perhaps. Perhaps we can push the envelope and make these methods cheaper to perform, make them more accurate, push the limits of efficiency. And then there's big math questions about the boundaries of applicability. What is the structure of a matrix that allows you to apply these methods successfully? What's the structure of a matrix that would definitely lead to failure? As the next frontier in randomized numerical linear algebra, in math, I think that mathematicians need to pay more attention to these Monte Carlo methods that are being developed in chemistry, because they are in principle applicable to all sorts of eigenvalue problems that show up everywhere. And the scaling with respect to dimensionality can sometimes be remarkable. So in quantum many-body problems in particular, there are folks who are trying to calculate eigenvalues for matrices as large as 10 to the 108 by 10 to the 108. And you all well know the reason for this scaling is because the basis in which the Hamiltonian matrix H is calculated will grow combinatorially with the number of electrons in an electronic structure problem, with the number of spins in a spin problem. And so if you assign just n electrons to m orbitals, m is a lot bigger than n, like a factor of 3 or 4, you get 10 to the 108 by 10 to the 108 pretty fast, with pretty mild numbers for m and n. You can assign n spins to plus or minus orientations, and that's easily 2 to the n basis elements. It grows really big, really fast. So we can't store a single vector of this size. That would be totally unmanageable. Here's a really simple example where I just like to look at these matrices. So this is a transverse field Ising model. It doesn't look too bad for 2 quantum spins. It's a 4x4 matrix. But then you go to 3 quantum spins, and now it's already an 8x8 matrix, and one can extrapolate further. It is large and it is sparse as you get bigger and bigger. For n spins, the matrix for this particular model problem has dimensions 2 to the n by 2 to the n, but there are just n plus 1 non-zero entries per column. And this large, sparse character is, really ubiquitous in a lot of quantum many-body problems. So maybe we can use the sparsity, although the largeness is going to be really bad. Traditional methods work well for non-extreme matrices. There are iterative eigenvalue solvers. There's a huge slew of possibilities: the power method, subspace iteration, the Lanczos algorithm, the Jacobi-Davidson method. But in this talk, I'll start with the simplest one, the oldest one, the power method. And the power method could be written as this 3-step procedure. You have a current iterate, xt. It's a big old vector. You divide by the Euclidean norm, so now it's Euclidean norm 1. This is like a normalization step. Multiply by the matrix A in question to get the next iterate, xt plus 1. And then, if you want kind of a slick way to do the eigenvalue estimate, take the inner product between xt and xt plus 1 at this step. So that's the power method. It gets you the maximum magnitude eigenvalue of this matrix A, assuming there's a gap. We can apply it to estimate the ground state for small systems. And we have to introduce a shift, right? So you apply the power method not to h, but to A is identity minus epsilon h for small enough epsilon. It's got to be small enough that the ground state corresponds to the maximum magnitude eigenvalue of A. And if we make it even a little bit smaller, A is going to be positive semi-definite or positive definite. But the problem with the power method, right, like no matter how you do it, no matter whether you start with just a single non-zero entry, is you get fill-in. So I said that for the quantum spin problem, there's n plus 1 non-zero entries per column. You start with order 1 non-zero entries, then you get order n, then you get order n squared, order n cubed, order n to the 4th. And after 5 iterations, it becomes unmanageable, right? So the fill-in problem seemingly just cannot be avoided, right? Like on the surface, whatever are we going to do? So how can we do it? How can we adapt the power method to larger matrices? That's the question that a lot of quantum chemists started to think about and came up with the most wonderful algorithms, which I'll review, and then I'll segue into our own particular take on how to do this maybe a little bit more efficiently or a little bit differently. The idea, which could be dated back to von Neumann and Ulam when they were first playing around with computers and thinking about how computers could work, is to introduce random walkers that hop all around on the different indices. So you're trying to solve a problem with a d by d matrix, and you've got d different indices, and you're going to get a walker that's hopping around to one of them at a time. Each walker is assigned either a positive or a negative sign. So I'm denoting the position with xi, ti, and then the sign with sti. Okay? Then in this method called full configuration interaction quantum Monte Carlo, these walkers interact in a game of birth, death, and annihilation. So it's an amazing game they're playing with one another. They're interacting. There's a loop where you look at every walker who's currently occupying a site j. And then there's some probability pjk that this walker is going to spawn other walkers at a new location differently from the one that's currently occupied. And the number of spawned walkers is some random whole number, njk. And here I've written a floor function, which gets you to the greatest integer that's less than or equal to the argument. This would be called like randomized rounding, what I'm doing here. I'm stating that njk is a whole number that's either just a little bit less or a little bit more than magnitude AJK over PJK. Okay, so maybe that quantity is like 1.5, you round up to 2 with half probability, you round down to 1 with half probability. This is a randomized rounding procedure. And then if AJK happened to be positive, you get the same sign as the parent. If AJK happens to be negative, you flip the sign. So that's the birth step. Then the death step, you're looping over the walkers, and you're replacing each walker that currently exists with some number of children on the same site, okay? So now we're not moving to new sites, we're staying at the same site. The number of children is a randomized rounding of the magnitude AJJ, and the signs of the children are the same sign as the parent if AJJ is positive, and they're the opposite sign from the parent if AJJ is negative. And then there's the coolest step, the annihilation step, where we cancel walkers on the same site with opposite signs. They annihilate each other. So it's maybe a very bloody type of procedure that's going on. There's birth, there's death, and there's annihilation. This is this amazing algorithm, which has been around for like 15 years now, that motivated us. 50 years. Okay, so there's all sorts of historical precedent, right? The 50s, right. So I guess the idea of having walkers is something that's common to many different communities. Like, this is a natural idea that might occur to many people at many points in history.
The first applications were in the 60s.
So hopefully this seems somewhat intelligible. The way that I like to make sense of it is I like to think it's approximating a matrix multiplication. It's randomly approximating a matrix multiplication where the vectors involved are these random vectors that are signed delta functions on the different occupied sites. And so you've got xt is the current vector of signed delta functions. Xt plus 1 is going to be the new vector that's going to be randomly chosen. And I claim to you that the procedure outlined on the previous slide enforces that the expectation value of xt plus 1 is axt. And even more than that, the birth step performs the multiplication with the off-diagonals. The death step performs the multiplication with the diagonal entries of A. And the annihilation step just performs the addition. A is the sum of the diagonal part and the off-diagonal part. So that's what's going on with FCI-QMC, with one caveat, which is that your population would randomly fluctuate if you tried this with almost any A matrix. If A is different than a column stochastic matrix, basically, you're going to get random fluctuations. And so what do? How do you control the populations from going to infinity or to 0 eventually? You have to do some sort of stabilization. And so FCI-QMC has this particular version of an adaptive shift, which is kind of clever, where you're going back to this formula A is identity minus epsilon Hamiltonian, and now you're saying actually it's epsilon H minus delta Ti, where delta T is the adaptive shift. It gets updated to kill off more walkers if their population is growing bigger, and to birth more walkers if their population has been declining of late. So this creates some stabilization. As a mathematician looking at this method, one question I'll get to on the other slide, but first I want to offer you guys a schematic. Sorry, I forgot I had this schematic, but I think this is helpful, okay? So this is taken from a paper in JCTC, I think. I just found it on the internet by Googling schematic for FCI-QMC, and I think it's really pretty good. You have 4 different sites that are indexed I, J, K, L, and then you've got some positive signed walkers, let's say, that are in orange, and some negative signed walkers that are in purple, right? And what you could see is you could see a little bit of death of the walker that's at site L, right? That guy's just dying off during the matrix multiplication. And you can see some birth. You can see some spawning of new walkers, especially from this I determinant to the j and k determinants. And you can imagine what comes next, right? Like next there's going to be the annihilation. On this particular j determinant, there is currently both purple and orange walkers, plus and minus signs. They have to annihilate each other. So this is hopefully a helpful schematic. But does it converge? That's the math question, right? It's beautiful. It's evocative. It's got a nice schematic. Does it converge? How would we expect it to converge? How could we study its convergence? That's actually a question that doesn't seem to have been handled very carefully in the literature. And I'll outline what we think happens. So we think that this whole system, if you view it as a giant, giant vector of all the current particle positions, all the current particle signs, and the adaptive shift, is a Markov chain. So given the current value, you can evolve it forward in time. We know from Markov chain class that many, many Markov chains, but not all, have a unique stationary measure, mu, and they converge to the stationary measure. Maybe geometrically fast in the language of mathematicians, maybe it takes a lot of time in practice. And if this happens, well, because of the dynamics, we are constantly pushing this vector of signed delta functions closer and closer toward the ground state through these repeated implicit multiplications with A. And so we would anticipate that this causes the expectation value under the stationary measure of x to be really pretty close to the ground state. Not right on it, because there's other things going on. I mean, there's this adaptive shift, for example. That's a little funky, but pretty close. And if this is true, then we can just estimate the ground state energy using the estimator that folks use in practice. They would call it a projective estimator. You would take a trajectory average of xs interproducted with a times some reference vector. And you would get a whole numerator term out. And that numerator over time would converge to ax ref times the expectation value under the stationary measure. And the same thing would happen with the denominator. You would take just an inner product with x ref. And indeed, you know, if the expectation value under mu of x is right next to the ground state, this will give you a good ground state eigenvalue estimate. So, you know, if the assumption particularly in 2 and 3 are correct, then you would anticipate 4 works just fine. And more precisely, you would anticipate a t to the negative a half convergence rate from a central limit theorem scaling with an asymptotic bias that depends on the Walker number. But, you know, a full proof is lacking.
Why do you say that? It seems obvious to us, I guess, that it will converge.
Well, which part?
Well, it's a Markov process. And so as long as you have ergodicity in your state space.
Right. There have been some papers, even on FCI QMC, that have proposed that the adaptive shift mechanism doesn't actually stabilize. And there have been other proposals in the literature that I've read that aim to fix the shift, to make the shift more stable in the long term. So that would be a critique from inside the community, where folks are saying that our formula for the adaptive shift isn't quite working. But then more technically, you know, you need a precisely stated regenerative condition. And for example, this clearly fails if A is block diagonal, right? You might not ever get from the one block that's currently being represented.
That's the ergodicity.
Right, so.
But you can, okay, the quantum chemistry is not so obvious, but in other areas, it is pretty clear that it's ergodic.
Right, so I would be worried about the shift running off to infinity, and I would be worried, you know, probably about the precise statement on the matrix A. I would maybe wager a hunch that you're right, that there is an irreducibility condition on A that would be sufficient if the shift were okay. I actually don't think the shift is okay. I think the critique is valid. That if people literally ran their FCI QMC forever, it would not stabilize. Yeah. Yeah, I think that the shift, if it were implemented just as I've outlined on the previous pages, would eventually cause the Walker population to go down to 0 or blow up.
Right.
If you were to simulate forever, let's say.
We actually analyze that as well as other people.
Mm-hmm.
And you can make a criteria on your shift so that it becomes exponentially small, probability of that happening.
Yeah.
And, you could say, what is the chance in, 10 to the 10th steps of it doing those things, and you make that small or whatever. Yeah.
Right, but if there is an exponential chance of it happening and you've actually got a mixing chain, then anything that ever could happen would eventually happen, right?
Well, you have to ask probabilities of it happening.
Right, so I would argue then that under the mathematical definition of geometric ergodicity, this algorithm isn't. Like, that would be my worry. And then, what basis do you have for anticipating a t to the negative a half convergence? It's sort of approximate. It's sort of like analogies.
I guess the other thing you care about is exactly how the convergence changes when you change the dimension, right? So it's not. I don't think in this case you're satisfied to just say it converges. You want to say something about whether this is a good idea or not, or as you increase the basis. Meaning that you need some precision in the statement.
Right.
So I think there's mysteries here. I mean, I think we could probably agree on that. What the mysteries are, folks might have differences of opinions. I'll ask a different question, though, and this will segue to the work that our group has done. Why not approximate xt plus 1 is axt more directly? Why go through this rigmarole of birth, death, and annihilation? Could there not be a more direct way to do things? And so an idea would be random sparsification. You can introduce a mathematical operator that gives random output. It maps a d vector to another d vector that has at most m non-zero entries, where m is a user set number, let's say 10 million. And the expectation value of phi x is x, so it's unbiased. In expectation, it doesn't change the input. If you've got this, then John Weir, my PhD advisor with Lei-Kang Lim, who's a numerical linear algebra expert, had a paper in 2017 that said, okay, well, we can normalize this time by dividing by the 1 norm of the current xt iterate. And then we can apply a randomized multiplication. Xt plus 1 is a phi xt. And this, because it is no longer a multiplication between a dense matrix, and a dense vector, now it's just a sparse vector, is going to be a whole lot cheaper. And you can control the computational cost by adjusting m. So raise m as much as you can afford it, or lower it if you can't afford it. Again, we can approximate the dominant eigenvalue using the formula from FCI-QMC. The projective estimator, where you take a trajectory average of all your XS iterates, interproducted with AXREF, divide it by the trajectory average, interproducted with XREF. Again, we anticipate a t to the negative a half convergence rate with an asymptotic bias that decreases as m increases. And the one twist is there's zero bias in this case. If m, the sparsity parameter, equals the ambient dimension d, there is no randomization. You preserve the exact input, so it's just the power method. The power method converges. So there's no bias. Yes?
Why are you dividing by the 1 norm and not the...
Well, it does a lot better in practice. Yeah. There's some aspects of this theory that, like the numerical results are remarkably clear about what you ought to be doing. And I would say maybe the math justification is a little bit harder. I have some explanation for that, but maybe not. It's not worth it. I got a lot to talk about. Yes?
So this division by 1 norm or 2 norm, whatever you choose, is that doing the same thing as population control in some sense?
Yeah.
So it is a bias.
Yeah. So we anticipate an asymptotic bias. that decreases as m increases, reaching the level 0 if you ever set m to be the ambient dimension. Yeah.
Okay.
Yep. Yeah, for sure. Tell me.
Do you affect the variance of the estimators when you introduce m sparsity?
Yeah.
Is it manageable or?
Yeah. So m, I mean, it remarkably cuts down on the variance as we increase m, right? So, we observe much faster than m to the negative a half scaling, right? We observe big jumps, right? Where like you get absolute rubbish when m's below a threshold. And then, you pick up m, multiply it by 2 or 10, and suddenly the algorithm gives you very sensible results. You'll see some plots, actually, which help to make that real in like 2 slides. There's a technical point here, which I loved working on, which is just like, how should we choose the sparsification operator? And I loved it because there's a well-formulated math question you could ask with a nice clean proof using convex analysis. For any x in Rd, so it's a d vector, the sparsification operator that minimizes the mean square perturbation magnitude is characterized as follows. And so, you can think about whether this is surprising or not as I reveal the 3 characterizations, okay? So will this surprise you, will this not? It probably depends on maybe what sort of randomization you've seen before and think is sensible. The largest magnitude entries are preserved exactly, okay? They aren't randomized. Just with probability 1, just keep them, don't change them. So phi x alpha I is x alpha I, where alpha is a permutation so that alpha 1 is the biggest magnitude entry, alpha 2 is the second biggest, alpha 3 is the third biggest. Keep them exactly as they were. The smallest magnitude entries are randomly perturbed in the following way. With some probability pi, increase them. Increase them by a multiplicative factor of 1 over pi. Otherwise, set them equal to 0. And the particular pi's have to be proportional to the magnitude xi. Lastly, last bit of the characterization is the number k of exact preservations should be as small as possible. Maybe you'd expect as big as possible. That's actually not quite right. As small as possible, while making sure that all the p's defined by this formula are less than or equal to 1. So that's what it is mathematically. It's a convex optimization problem when you look at it the right way. Here's the cartoon. You've got here a 6 vector. Am I counting right? 7 vector. Oh, groovy. Okay, so you got a 7 vector with 1 big entry that gets preserved exactly, and then there's 4 small entries. And so in particular, you are going to, with probability 1/5, sample this entry here, or this entry here, and with probability 2/5, sample this entry. But whichever one you pick, you are going to round it to 0.25 or minus 0.25, depending on the sign. So this is interesting. It mixes deterministic math and random sampling math. So it is sort of properly a Monte Carlo algorithm because of the random sampling. But it's also got a deterministic component, and that really helps. That really, really helps. Here's what the algorithm looks like, the whole thing, the FRI algorithm on a pretty small system. We wanted to just look at what happens when you increase m, increase the number of non-zero entries from 5,000 to 10,000 to 50,000. And you're seeing this crazy wave in like teal of what happens when m is 5,000. The average estimator is just going up and down and all over the place, and the accuracy is atrocious. And then you just double it, and the error bars go way down, right? Way down, way more than 1 over square root of 2, which is what you would anticipate from the normal Monte Carlo m to the negative a half scaling. And then you increase it to 50,000, and it's like almost impossible to see what happens with m equals 50,000 because everything in this plot is just compactified around some purple line that's just nicely decaying.
Can I ask?
Yeah.
So with this neon example,
Yeah, sure.
you have something like 50,000 elements that you're treating exactly. Is that right?
No, that's not right. Every vector iterate has 50,000 non-zeros, a small fraction of which would have been deterministically preserved, and a much larger fraction of which would have been randomly sampled in practice.
But in each step, you do a different random sample.
Yeah, it's independent at every iteration. Yeah, given the current information, just independently apply the algorithm outlined before. Yeah. So it's fascinating.
Can I ask another question?
Yeah, for sure.
So when you are updating some small number of random, or like whatever number of random, like round up and down, do you have population mixing of now one of those is in the list of k fixed values? Like, can you, or does it always that your rounded numbers stay below like the churn, and there's a certain subset that are never?
So this would be maybe a greedy algorithm. You could think of it this way. It's a greedy algorithm in the sense that it just currently looks at the magnitude and picks off the current biggest magnitude guys. There's no history whatsoever, so you can't get added to a list. You can't get added to a list. You could have been huge last iteration and then be tiny this iteration, and you'd be randomly sampled. So in particular, this would not preserve non-zero in the Hartree-Fock determinant. It would not preserve that, actually. So.
Isn't that a problem? That's what I was asking last time. If your energy evaluation is with respect to Hartree-Fock.
Well, we actually use slightly better reference.
Let's say whatever the reference is, as long as the reference is, let's say, 5 determinants or whatever it is, if it is truly randomized that they can all fall out of 0, then then it's a problem.
You're a little bit saved, though, because of the averaging. So as long as, there's at one of these iterations.
So you're averaging all the denominators.
Yeah, if there's an overlap with Hartree-Fock at one of these iterations, right, then you're going to be okay. You're going to have a non-zero denominator. We usually have overlap with Hartree-Fock. I'm just explaining because I think it answers your question, that in principle, one could lose overlap with Hartree-Fock, that there is absolutely no list. Yeah.
But presumably you could not do that. That's the reason we choose. So presumably you could designate Hartree-Fock.
Yeah.
Small number. So there's probably a reason that you're not doing it.
Yeah, we tried it and we didn't get great results.
But formally, there isn't any.
No, we even tried it. We thought it would work. I think we were surprised. We picked from singles, doubles, and perturbative triples, what are some of the biggest magnitude entries in the represented ground state. And we thought, let's treat them as a deterministic subspace that we always try to treat deterministically. And we just found that it didn't particularly improve our results. Made the algorithm more complicated. We were surprised. And it could be system dependent, but it's just you try building in this extra piece to your algorithm, it doesn't work well the first 3 times. What's the motivation to keep trying? Yes?
So in this algorithm, sorry.
Yeah, we're good. I'm going to get through it.
So in this algorithm, you have this normalization step.
Yeah, for sure.
If you got rid of it, what happens to the results?
Yeah, it goes to infinity or 0 in terms of Euclidean norm. And the averaging is completely crazy at that point because let's say it goes to infinity, you would disregard all the early information. You would just be paying attention. Oh, the norm of your current xt. If you do not apply normalization, periodically to your xt,
so let's say A is you chose A, which has you deterministically made the A minus ground state such that in deterministic calculation the wave function would stay normalized. So in that case also you would get some problems.
Yeah, the randomization would lead to random fluctuations. Yeah, with one kind of trivial exception, which is if A were actually kind of column stochastic and kind of positive, sometimes you can get it so that X is always summing to 1, right? And then you don't need the normalization. That's sort of like a stochastic Markov chain Monte Carlo evolution. But that's the only case, and that's never what happens in quantum chemistry matrices. Yeah.
This is what we used to call the Combe method.
The comb method. Yeah, this is the comb. This is the comb. Yeah. It doesn't get called that much anymore. It's called resampling. But I like the comb because it's kind of evocative. Yeah. I want to get to excited states. And so let's see what I can do. I think I'll be able to do a pretty good treatment. Yeah, we wanted to do the simplest version of FRI that I outlined for you above, the simplest version of FCI-QMC, and compare them. And the results were very favorable for FRI. But like you'll see as I get to the last slides, that the real practical versions of FCI-QMC and FRI implement two other things, which should be like random matrix multiplication, firstly, and secondly, an initiator approximation that diverge from the simple algorithm I just introduced. So this maybe gets at the mathematical heart of things, that there's some potential for FRI to do well. Per iteration, you're getting much, much lower variance. Here, statistical efficiency is the inverse of variance. That's how we define it. And there's other questions too. I mean, there's questions about, how quickly with modern parallel computing architectures can you actually implement FRI and FCI-QMC? And this simplified comparison doesn't take those things into account either. This is just literally do the simple algorithms I outlined on the previous slide exactly as I stated them. Look at 1 over the variance. FRI is a whole lot better. Subspace iteration is the generalization of the power method to k bigger than 1 eigenvalues. It looks a lot like the power method. The first step, again, is going to be a normalization step. It's typically accomplished through a QR factorization of the matrix xt, which is d by k. So you get xt is qt, rt, where q is an orthogonal matrix and r is upper triangular. And then you perform a matrix multiplication. Xt plus 1 is a qt. And to compute the eigenvalues, you can just look at qt star xt plus 1. So it's iterative, just like the power method. Go 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Get better and better eigenvalue estimates. And these steps are, again, normalization, multiplication, estimation. Normalization, multiplication, estimation. Normalization, multiplication, estimation. xt can be written using this explicit formula, which takes advantage of the r factors introduced on line 1. xt is exactly equal to atx0. So that's multiplying your starting matrix by some giant, giant multiple of a. And then a whole bunch of normalization steps. So it's got the right span that you would get from multiplying x0 by a to the tth power, but it doesn't all degenerate onto just the ground state. Rather, the normalization is really keeping it from that degeneracy. And again, this is a d by k, really, really tall, really, really skinny matrix. Eigenvalue estimates converge surprisingly fast. When I saw this result and tried to justify it to myself, it took me forever. I eventually learned the trick. What's interesting is not the 2 to the t, because you would expect that from the power method with the estimator that we're using. What's interesting is the particular spectral gap that arises when you're estimating the ith eigenvalue is the relative spectral gap between the ith eigenvalue inside your subspace and the k plus first eigenvalue, which is the first one outside of your subspace. So that means you're going to get much faster rates for eigenvalue 1 as compared to eigenvalue 2, because eigenvalue 1's got the biggest gap, right? So you're going to get the fastest convergence of the ground state energy and then the next fastest for the first excited state, and so on, down to the kth eigenvalue. So really cool. This is in one of your papers? Oh yeah, it's a beautiful result. I mean, how interesting, and yeah. And I really had to work around for the math trick. Like it's a cool argument. Yeah. We're gonna FRI-ize it. We're gonna apply the FRI ideas to subspace iteration. To reduce the cost, to get rid of these multiplications with dense matrices that would arise as a result of fill-in, we are going to apply a random Sparsification operator in step 2. And that means apply it independently to every column. So we'll apply some stabilization where we get out a QT matrix that's a little bit stabilized from XT. We'll apply a matrix multiplication. XT plus 1 is A phi QT. And then approximate eigenvalues using the generalization of the projective estimator from the FRI power method. Right, so here it's a generalized eigenvalue problem. And you would get out K eigenvalue estimates this way. You'd also get out eigenvector estimates if you wanted them, but we've not looked at the accuracy of those yet. The question you might ask is, what is step 1? I've changed the language a bit. Before I was fully explicit, I said do a QR factorization and grab the Q factor. Now I'm using softer language, stabilization. And I'm just saying QT is XT times some UT matrix. Okay, so the span of the columns is not changing, but the columns themselves, are they orthogonal? Are they nearly orthogonal? Do they have different Euclidean norms? We shouldn't fully orthogonalize QT at every step, because empirically it causes big random errors. So we tried it. We have it in an appendix of our paper because you don't want to show people in the body of a paper bad results where a method fails catastrophically. They will invariably confuse it with your method and think that your method fails. So okay, we tried it. It doesn't work. Rather, what works is instead we orthogonalize xref star qt. So we're orthogonalizing not the full columns, but rather their inner product with some other reference matrix. And we're only doing it occasionally. We're only doing it when the condition number is starting to rise. So when the columns are starting to get ill-conditioned, linearly aligned with one another. It turns out to be 1,000 iterations in the test systems that we used with the epsilon parameters that we used. Although we do anticipate that this number would be way different depending on the spectral decay properties of your matrix A.
What's the 1,000 iterations is surprising. This same problem happens in AFQMC where the columns start to but you have to orthogonalize much more often. 1,000
Yeah, doesn't it seem long? Like, isn't that crazy? Although it is.
Pick the counts are very different.
Huh?
Because there you have many counts.
This is very system dependent, I would guess. But
Yeah.
If you're looking for low-lying conditions, you have
Okay, so you have fewer columns. Okay, sorry, go on.
No, we're doing good. We actually have 5 minutes, and I've got like 5 minutes left. So we're rocking and rolling, thankfully.
Unless we have a long break. So
Oh, yeah, cool. At other iterations, we normalize the columns, but don't orthogonalize. So that means you make sure that like their one norm is stable, but you don't linearly combine them with each other to make them orthogonal.
Isn't there also some effort needed just to know what the condition number is? We have to sample this overlap. Also,
Which step are you talking about?
so just to compute this overlap matrix.
The xref star qt?
Yeah.
We choose xref to be pretty sparse, right? So you don't want to just do Hartree-Fock, right? You want to do something that's a little bit better representation of...
Still not that sparse.
Yeah, so there's a balance. You know, choosing xref, you have to balance sparsity, right, with accuracy. And, you know, I'm clearly the person who's worked on theorems for this paper. I'm not the one with the extensive knowledge of full configuration interaction. But I know that Tim Birkelbach found sort of some particular approximations that seem to be the right balance between sparsity and accuracy. And he used them systematically throughout our work.
Is there a recipe for using xref, or is like this?
Oh, so the better you choose xref, the closer to the actual ground state and low-lying eigenstates, the more accurate your eigenvalue estimates will be.
But also you want to keep it sparse
Yes.
so that this thing, the computation, possible.
Exactly.
Very fine balance and their recipe.
What did we do, John? Do you remember?
In the last paper, Sam used HCI.
Or excited states too.
Yeah.
There we go. We used HCI.
I don't remember actually.
Yeah.
Look.
Yeah.
I guess that form, there's fast evaluation.
Yeah. So it's a balancing act, though. I mean, that's totally right, Lynn. Like, you've got the dominant trade-off between accuracy and cost. Quickly, results, and then conclusion. So I like this. I mean, this was an easy test system, but what it illustrates is that the randomized algorithm, if you don't do the averaging, which you always want to do, but if you didn't do the averaging, you would find that the instantaneous energy estimates track the deterministic algorithm for the first 1,000 or 2,000 iterates. These random instantaneous energy estimates are right on top of the deterministic ones. And then the deterministic ones continue to go down with the rate that I kind of indicated in a few slides below, the deterministic rate that we know well. Whereas the randomized energy estimates will start to get really wiggly because of the random variations. Averaging in the way that I outlined would get rid of the wiggles. But it wouldn't be as accurate as the deterministic method. We never claim that we're as accurate in the long run as the deterministic method. Oh, geez. OK, I did forget about this part. I'm going to breeze through it. We incorporate two more tricks. This is the FCI-QMC-ization of subspace iteration. These are some tricks we borrowed from FCI-QMC, OK, which are really important for scaling up. First trick is randomized multiplication. So instead of actually doing xt plus 1 is a phi qt, you do this crazy sequence of matrix multiplications and sparsifications, where the first matrix B1 is a selection probability matrix for single versus double excitations. B2 is first occupied orbital. B3 is the second occupied orbital. B4 is the first virtual orbital. And B5 is the second virtual orbital. You perform this sequence of multiplications with these selection probability matrices, randomly sparsifying after every turn. And then lastly, you multiply with A prime, which gets rid of the bias. So it has elements Aij divided by the selection probability of going from I to j. That's the first trick. I know it's a lot. I'm just rushing to give you the whole picture. Increases the variance, but speeds up the computation considerably, because no longer are you looking up whole columns. Second, initiator approximation. Instead of doing this whole multiplication, sometimes you don't. Sometimes you just resolve this particular part of the matrix multiplication, the ij term times the jk term, by forgetting about the off-diagonal elements. Just look at the diagonal elements in the randomized multiplication, and you only look at the off-diagonals if you are bigger than some threshold in magnitude. That's called the initiator approximation, and that one contributes a small bias but reduces the variance. Both of these tricks are really necessary for scaling up. Here's the largest systems where we've applied the excited state methods. On the left, you've got a compound we're calling, oh gosh, yeah, thank you so much. I appreciate you. And then on the right, we got ozone. That one I know well. And you know, we're just showing that we can compete with HCI if we set the number of walkers or the sparsity threshold high enough. We're showing that, yeah, our method converges as you raise the number of walkers. And we're not claiming that we're outperforming HCI. We're claiming, though, that our method is indeed, like the theory would predict, systematically improvable by increasing M, and that it's getting the right answer for multiple excited states for these two particular systems. And the summary is we've applied FRI to estimate ground and excited state energies now, and in 4 papers for small molecules. It's been pretty promising. In particular, these applications I showed you on the previous slide, we're pretty sure these are the largest excited state calculations that have been done with FCI-QMC or FRI. So there's other methods that would typically be used for excited state calculations. You know, we saw HCI performing very well, for example. But what we've fundamentally done is come up with a pretty good way that these methods could start handling excited state calculations. We've used a particular normalization that's pretty stable that allows people to start doing these excited state calculations. And lastly, I would say these are theoretically interesting to a mathematician like me. There's a lot of room for further development of these ideas for extensions beyond quantum chemistry. And I think there's, some really glorious math questions that are really being revealed through these algorithms. And I want to thank you for your attention, and I know I'm a little over, but if anyone wants to stick around, I'll help.